Yes. So, as I said, I want to let me remove this thing. I want to very quickly go through the functionality of SVM in a kind of recap mode and make some last notes before we continue with the next topic, which is constructing word embeddings. I mean, the problematic of constructing word embeddings. Right. Here we are. Exemplified on a binary classification example. Oops, sorry, that's supposed to be my son. Right. We have two classes, supervised learning, and we talk about model-based classification. So we want to build a model that takes input that takes initial feature vector as an input and provides a recommendation for the category, either negative or positive class. And we are talking about a linear classification case. It means that our feature vectors, in this case exemplified by two features, x1, x2, are separated by a line, which is maybe not the case in many practical cases, but linear models, you will be surprised, they receive increasing attentions even today. Why? Because they are simple for training and simple for executions. And we are talking about constructing such a model, and for this we take parametric equation for a line, and we try to fit this line in between samples of the two classes, and we do it geometrically. So that's what I like about SVM. So it's very intuitive from the presentation perspective. So you take samples, you compute the distance to the line, to the model, and you try to maximize this distance. And as a result of definition of the optimization problem, so we move first from maximizing the distance to a problem of minimizing the inverse of it. So that was the first step. And this comes from the line equation, and V are W's are coefficients of our model that we want to build. Plus, we have constraints, so that all samples of the positive class they should be classified as positive values, and the negative class as less than one, basically. Yeah, and this is the same notation for this system of constraints. Then what we do, so in this way, so this is an optimization process that we can attempt solving straight away. However, so we would take a different approach. So and the idea with this approach is to convert to a dual problem where we get rid of weights. So for samples, or not weight, sorry, coefficients of the model. So we do not try to tune the coefficients of the model. Rather, so we basically convert to a task with reduced number of parameters to optimize. And we do it by first by applying Lagrangian method. So constructing a dual problem, so where we have our optimization function and our constraints in this form. And the dual conversion to the dual problem happens when we take a derivative and making to zero. So when derivative equals to zero, so then we found the minimum. And we take derivative by partial derivative by coefficients W and bias B. So these are the unknowns for our case. So when we do take this derivative of this equation now, or of this formula here, so we got the following. So this is the derivative, partial derivative with respect to W's, and this is the partial derivative with respect to B. And we make them zero. This is a part of our dual problem definition. And then we substitute this things, so the expression for coefficients into the original formula here. And after some simplification, you get this dual problem formulation. So what is good about it? As I said, we got rid of coefficients W and B, so and only have coefficients which are in front of each sample. So basically, how sample contributes to the overall model. So we don't, and here we have also a dot product between pairs of samples. So at this point, so I want to ask a question to you. So what is the bottleneck of this method? I mean, as we see now. N squared complexity. Yes. So and with respect to number of samples, so it is over here, this dot product. So to enable optimization, to solve this problem, so you need to compute pairwise similarities between samples. And obviously, the larger you have data set you have, the larger is this matrix, this of dot products. And yeah, and that was and is the main kind of computational bottleneck for SVMs. Yes, but let's. I will address now the ways how people approach overcoming this. Oops, what did I do? I didn't do anything. Okay. But first, I want to that's what we left off with last time. So now you solve this problem, this dual problem, by usual numerical methods, finding coefficients alpha. So when a dual problem is solved, then you have very few alphas that are larger than zero. Mhm. well, we have as many alphas as number of samples, obviously, but very few alpha I which are larger than zeros. And those are dual coefficients for support vectors. So those are the samples that contribute to computing the model. And these are the coefficients that you extract in your lab one, even after training. But what do you do with them? You actually take these coefficients and compute W and B. So the vector of W and B. So now remember that so W's is a vector of individual weights of individual contributions of features, and B is a bias parameter. So our model, so we compute this for our model, which is F equals W X plus B. So this is our final destination, so to say. And to do that, so you go back to part of the definition of the dual problem and use this to compute the weights. Y I X I, and here you have what is it? I goes from 1 to n. This is the number of samples.
It's alpha y and x, right?
Yeah?
Alpha y x, or is it L?
This one.
No, that one. Is that alpha?
Alpha. Alpha.
It's
So the coefficients. So in this way you compute W. As for the B, so so now I just want to remind you. So you have this samples of one class. So these are your support vectors. And you're computing B for this line. So this is your F. And for that, you need to remember the following. So it's part of your conditions. That's yi wx I. So that's vector plus b equals 1. So what you can do, you can multiply both the left-hand side and the right-hand side by y. And then you got the following, yi square w x I plus b equals y I. Now, what is yi? Can you remind me? Exactly. These are labels, -1 and 1. So this thing becomes 1. And and then your b is simply yi minus wxi. So the vector w computed above, x, y you know, yi you know. And what you do, you compute b for all samples of support vectors and average, take a mean. So then your model is complete. So that is the final model that is used for classification. So pretty much similar equation. Yes. And then, well, I will not go into this topic, but there are two options to go from a binary classification case to multi-class classification. So, so one versus rest and pairwise classification, basically. And so that you tried in lab one. Now, the concluding note on this topic. I mean, actually, this method, support vector machines, it was, well, it is one of fundamental methods in machine learning, as it is based on solid mathematical apparatus. And I want to go back to this definition of the dual problem that we actually solved to understand the support vectors, and want to draw your attention to this part of it, so which is the dot product. So essentially, so this problem means that you operate in a space of similarities between pairwise similarities between samples. So so now remember that let's talk about the following. So that's so far we talked about SVM in the context of linear classification. In for linearly separated data. Separable. So that was our starting point. So you have category 1, category 2. And then, so there is a strict border between these two categories, and it can be modeled as a hyperplane. So hyperplane is a linear model of dimension n-1 if you're with respect to the dimensionality of data. However, many cases, for many cases, so this doesn't hold. So, and one of these toy examples that normally used to illustrate this is when a category is located within another category. So so as it is shown here. So obviously, so there is no way in this very case to draw a hyperplane, or in two-dimensional case, hyperplane is a line. So shall we give up or what? What shall we do here? apparently, people came to understanding that the data can be analyzed, including the interactions between features. So some distinctive properties, so that allow them to be differentiated, I mean, these categories, can be discovered by looking at next level interaction. So how, for example, so if we have originally features x, x1, x2, so our x, so sample x is described by two features on x1, x2, say temperature and pressure. So, and in this case, it might well happen that the data is not linearly separable. However, again, so it was discovered that maybe if you would look at interactions, so for example, if you take some and compute some function of the features and add it to as a new feature, so you expand the dimensionality. So the problem may reveal different properties, so to say. And that what is normally demonstrated in this very case by adding a third dimensionality. So consider x star, where you have original features and their next level interaction. So let's put it a general form. F of x of x, or maybe another level of interaction. So they can be so interaction between so let's say another function g of f of x and x, like that. So as an example of this phenomena, so let's assume that our x star would be x1, x2, and x1 square plus x2 square. So this is a typical toy example to demonstrate this phenomenon. Now, obviously, you need to add a third dimension. So you have your original features, x1, x2, and that would be x square plus x1 square, x2 square. And when you do that, so you can see that this very case in the dimension 2 plus 1, which is equal to 3, forms a paraboloid, so a shape, a three-dimensional shape. So where these outer samples are located somewhat above the inner samples. So, and we did this by pure mathematical transformation or synthetic creation of a synthetic feature. So, sorry for that. Which is computed by taking next level interaction between original features. So in this case, polynomial. So it's sum of squares of original features. It can be different functions. And depending on this function, so you will have different different transformations, relative transformations. But what is actually transformed here, if you think about it, so by doing this manipulations, you transform the relative similarity. So apparently, similarity between these guys over here. So the similarity of one category become conserved within this area, while and it means that it will be substantially more different from the similarity between this outer circle. So you modified the internal properties of data. And in this very case, it just is easy to visualize. So you kind of really moved one set of samples above the other. And in this case, it becomes linearly separable. So you can draw a plane separating these categories. So all this long story short, by doing this, so we doing this modification, in general, we introduce a function that modifies the dot product between the samples. And such function that actually modifies dot product by adding extra dimensionalities is called the kernel. And transforms dot. This is very informal definition, so no pretension to be exact. Transforms yeah, dot product when mapping to higher dimensions. So two things are here. First, a mapping functionality. So you take original data, you do some manipulation with it, and as a result of this manipulation, you add extra dimensionality. So this is one thing. But by doing this, you also implement a function, some function that modifies the relative similarity between samples. And this function is called kernel. So a little bit more formally. So you take your original features from the original domain and the original dimensionality. And you produce new features, so XStar, by applying certain transformations or feature map in general feature map. So you take original features, apply this transformation, and this x prime now, x star now belongs to Rn, and n, where n is much larger than d. Yeah, so that is the property. So there are some theorems proven on this matter, but what concerns us is the effect. So we can massage the original space given us by features such that we modify how it looks for our classifier, and that is a useful thing to have. What was found in the context of support vector machines, yeah, I will come back to what was found. First, a commentary about this transformation. So compare it to this toy example. In many real examples, this mapping functionality is not trivial at all. There are fundamental theorems that tells that this effect is achievable when you expand the dimensionalities up to infinity. So that makes it very problematic for us for practical usage. So infinite dimensions are tricky to handle if complexity of SVM is n square in addition to this. But I mean, as a continuation of these theorems, it was found that in fact it is not necessary to do this transformation. So you can apply a function directly to the dot product, to the similarity, because at the end, so if you look at the definition of kernel, so we take the first part of it. So it's by doing this mapping, we introduce a function that modifies the dot product between pairs. And that was utilized in something that is called kernel trick. So and very briefly, so it is about take L prime, so the dual problem. And so identify this dot product stuff, xi dot xj. So this is the dot product. And well, in the plain case, you just leave it as it is, or under the kernel trick, you actually apply a function. Okay, xi dot xj. So where k is a kernel function. So and now what are the kernel functions? So there can be different and so they just to list what is available are linear. So that's the one that we had. Polynomial, Gaussian, sigmoid. Well, many functions are possible. and they do modify somehow the original dot product in some nonlinear way, hoping that it become this is the key word, that the case become closer to linear separability. So in principle, in practice, you need to. It's up to the experience of the engineer to choose one of these functions. Yes. And that's what you tried in Lab 1. So, as you see, I hope you see it now. So, starting from very intuitive geometric formulation of a classification task in a supervised learning context, we built again geometric model for a classification on the one hand. So we solved that. Converting it to a dual problem and kind of let it be. Independently, we talked about just general properties of data. So with respect to the reciprocity. So what from your previous machine learning courses, you know that so what neural networks do by this massive training, so they try to build this kind of very, very fine nonlinear boundary between the categories. But for this, you need to actually set all this multitude of parameters. So here we have a different approach, which actually makes sense. So what if we modify the data so that it becomes tractable? So that's important to remember. And we do it by means of introducing a kernel function that modifies the pairwise similarities. The last word, I definitely, I mean, I should spend more time on it because it's practically interesting and useful. It's not the end of the story. So SVM still suffers from this quadratic complexity problem, and again, it was if you look at the timeline, so SVM was introduced back in 90s. So computational powers was like none compared to today's, and it was really a big problem solving this large optimization problems. So now it's less critical in computational power from the computing power point perspective, but still, it's one of the main bottlenecks of SVM. What, as I said, so what is the continuation of this story? So as I told you, so originally it was found that this kernel function can be implemented by mapping the original features into infinitely dimensional space, which is impractical. But then later on, back in beginning of 2000, like 2005 or so, several methods appeared when of explicit kernel transformation. So explicit dimensionality expansion. So and that's a kind of interesting thing. So we in the context of machine learning, people normally talk about dimensionality reduction. So you take and that makes sense, obviously, to remove highly correlated feature. But when you're done with that, still you are left with a high dimensional data. And the way to massage it, so to say, is again expanded, but now including the interactions between features in one way or another. So one of such methods, and again, if you are interested, you can contact me separately. One of such methods is known as random Fourier features. So let me just finish this topic by kind of dumping this possibility on you, and we come back to it maybe in one class from now. So the idea expand so that dot pro is modified. And so my the area of my research, which is hyperdimensional computing, it also falls into this class of expanding dimensionality. So we will talk about these topics a bit later. So, but the idea is that you, yeah, that's important thing. Still, key thing, dimensionality finite. Yes. So I leave it with you for a moment, then we'll see if we have time to talk more about it. Break, pause, 5 minutes, just to swap the topics. Yes, in the second half of today's class, we will be talking about aspects of NLP. You know, NLP is huge. Yeah, we can identify several courses, standalone courses on just the formulation of the problem, different tasks, a separate course about ChatGPT and such. Here, again, so I want to kind of contrast the neural network-based methods to some alternatives when constructing embeddings. So, and to do this, we need to be on the same page and just agree on the terminology first. We talk about just common NLP tasks and focus again on embeddings and different simple models that you can use for your purposes. NLP, super important because we use language for communicating information, and this is probably the fundamental aspect of human intelligence, so that we are able to communicate and comprehend, not only communicate and before all comprehend verbal information. So it means of collaboration and conveying information. The tasks that we will consider, well, in this course are amongst common tasks in natural language processing. For example, to classify a genre of a text, so comedy, drama, whatever, news, etc. Another task would be to identify language. Given a text, determine in what language, in what natural language it is written in. Spam detection. So there are different ways of approaching solving this problem, and which require uh, kind of more or less sophisticated insights into the structure of the language. So language is a very difficult or complicated matter to model. Many tasks concerned with somehow modeling, not understanding is not correct word, but modeling of meaning. So like finding synonyms. So and here we somehow want to find words with similar meanings, but written in a different way. And meaning is needed in different contexts. So first to automatically process text, obviously, but if we turn the things around, so again, if we talk about human-computer interaction, so these are the means again to communicate information back to humans. So one example of so I was partially involved in a bigger study with my partners in La Trobe University. So they studied, for example, blogs of post-cancer patients. And again, so they tried to solve a particular task of identifying emotions and tendencies towards a worsening of psychological state by identifying the patterns of collection of phrases that could be attributed to, for example, state of depression and such. So this many socially important tasks require understanding of natural language. Modeling meaning, this is a more fundamental challenge than just of a natural language processing. So how to model meanings of things so it can be processed by machines. This is not a topic of this class, so you can find these books or this book. Yeah, these are both about the same topic about conceptual spaces or geometry of meaning. So actually, they were written by Swedish scientists from Lund. So he is now retired but still active, Peter Edenfors. An interesting approach. So think about it. Another reference connected to this I want to give you is this article over here. It's from last year. I read it this year, and I found it extremely interesting in the context of today's discussions and slash speculations around ChatGPT and such. So it's published in Philosophical Transactions of the Royal Society, and it's about fundamental challenges of artificial intelligence, about learning symbolic representations, learning compositional representations, and symbol grounding. So these are three not fully resolved challenges of AI. I will put PDF with the link to Canvas so you can read it offline. So why am I referencing it in this context? As I said, these large language models or the product based on them, like ChatGPT and such. They're indeed incredible, so in their capabilities of exposing human level type of interaction and reasoning on different topics. But then the question is how systematically they address the concrete challenges. That remains an open question. And this is not an article that criticizes LLMs. Rather, it is a rather pragmatic approach of seeing, I mean, what part of this fundamental challenges are addressed by LLMs and what not. So, if an example of reasoning presented in this paper is the entire concept of symbol grounding. So symbol grounding is making a connection from a physical percepts to symbolic representations. In neural networks, they are known that addressing this challenge natively. So they say take any visual computer vision model. So it kind of you present raw pixels, and it outputs like categories. So by this, you do this. You establish this link. Large language models, they are trained entirely on texts, on textual information, and at the same time, so they presumably learn symbolic like representations of objects. So what is how about grounding in this case? Shall it be redefined or something? So if you want to know more, so as I said, so this would be a topic for an entirely different course. But I really recommend you to read this article and the references within, so which point back to 1980s and such. And conceptual spaces. So we will be concerned by very kind of naive way of capturing meaning in terms of, for example, finding synonyms. So we will we will try somehow. Wait. We will try to create such word embeddings or representation of words so that words with a similar meaning somehow become clustered together with respect to, again, a chosen measure of similarity, cosine similarity or dot product. That you will try in the lab. And I mean, just focusing on this very simple task, machine learning does really great success. So it really beats above average humans on TOEFL test synonyms. Again, so language. What does it mean to model a language? Language is a really complicated beast, so to say. And so if you ever read about all the complexities of large language models, that's probably the most so far comprehensive and model of a language. But depending on the task, your model can be made much simpler. And that's what, again, so in the machine learning context, you are searching for methods which are with a good balance between computational complexity and the performance on a downstream task. So we will focus on a simple language model based on n-gram statistics. And This model was known since a long time ago, even before before computers were invented. So and it's about checking the statistics of different combinations of letters, syllables, or even words. So this model is applicable on different levels of granularity. And this model is surprisingly good for different tasks. What you will do as part of lab 3, you will use this model to classify text in 21 European languages. So now I don't know if the one who asked this question on Discord is present, but if not, I will repeat it again on Discord. I want to make a detour and go back to Canvas and do some clarifications on lab 3. And by the way, please be sure that you use the latest version. So I modified it slightly to remove some ambiguities in the previous version of the document. But I will tell you what it is all about. I will be talking about the methods you will use in this lab. What? Yes. During the next class, today I just want to maybe clarify a little bit on how you work with the data set. First of all, so in this task, so you have to prepare data set by yourself based on the input from the internet. So you need, for starters, you need to download samples of text in 21 European languages, and this, unfortunately, or I don't know, not unfortunately, but this you have to do manually. So the link brings you to this page, and what you do, so all languages are listed here. So Bulgarian, Czech, Danish, German, Greek, English, Estonian, etc., etc. So you go here, so you select all languages and say we want Bulgarian here. So then you come to this page, and again, so here it's important that I specify, so it wasn't part of the previous description, unfortunately, but now it is. So you need to select news, corpora, text corpora from news part. So here there are different sections, like from news scroll, Wikipedia. You select from news. Then, so there are different options in terms of number of samples you have. So again, I didn't specify which one. So you select the one that you think is appropriate. So obviously, I mean, more entries requires more processing. So maybe you can start with some simpler, smaller data sets. And again, I don't specify which year. You are free to choose any year. So when you so you click on it, so you download download part of the data set. And so here you have different files, but you are interested in sentences. So there are different. Well, you can check what these different files are, but you need to locate you need to locate the text itself. So this is the, Bulgarian. So you can also, and then you need to do the same for other 20 languages of news. In addition to this, you can, for task number 3, so you can you download data from recordings of European Parliament sessions. Oh, it was available. Um, Here. So you have all the corpora here. So again, you download and then you choose corresponding sentences for your language. And then as part of lab 3, what you so you need to implement that model that I described in the lab. Before that, you need to do quite some pre-processing of text to homogenize it, remove punctuations. Bulgarian needs to be converted to Latin and such. But again, so it will be fun, but lots of work. And then as part of the lab, so you train your model. You first test it on the same data that you used for training, so on the news corpora, by doing proper splitting of the data set. But final testing you do on the Euro Parliament data. And then normally you see some degraded performance because, I mean, it wasn't part of training at all.
Do we pick just one from them, or do we pick every 18 of the different?
Say again.
The Europarlament has 18 different data sets. I believe Hungarian to English, Swedish to English. Do we just pick one, or do we take all 18?
21. Yeah. Are they 18?
When I count them last, it was
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 20. Something is missing here, or I counted wrong, but it should be. I mean, check the languages. I mean, they should be kind of coincide with those that you use. Yeah. Right. So that was about logistics of the lab. But back to this business. So we in any case we are or for many tasks. In addition, so you can build a language level model. So that is about, for example, using n-gram statistics, or you can build word level models. And in this case, we are talking about producing an embedding of words. So in a general case, embedding is a transformation from otherwise very large, sparse space. So where you have the dimensionality of the space is the number of words in a dictionary with 1-hot encoding for each, into a vector with much smaller dimensionality. And in this target space, so the embedding should reflect on semantics on the meaning of the words. So similar words with similar meanings should be clustered together. And for assessing this, you use similarity measures. So there are different measures for this. So you can use also distances, but um, similarity measures such as cosine and dot product are more appropriate in this case. Sorry. Some boards, maybe I should stop it and instead go into details. Let me just scroll. So this is about you can read offline and also find on the internet the way how to assess the quality of embedding. So I mean, as you can imagine, there can be multiple transformations from this original space of vocabulary vectors into embeddings, but you need to address the quality, assess the quality. And for this, there are different methods on how to do that, how to evaluate board embedding. So, which basically fall into one of the two classes when you use some downstream task or just use for direct comparison. We are concerned with two alternatives for creating embeddings. One, embedding or models of words. One which is called connectionist way. So basically embeddings produced by training a neural network in a special regime, and a distributional model. So that's an alternative method that you start looking at in lab 2, so and continue working with in lab 3. So and hope again, so you can see that the idea is to show you that there are different competing approaches. Sometimes there are computationally simpler models that achieve similar performance compared to neural networks based approach. So the idea with connectionist model is rather straightforward. You have a neural network, and there are different configurations of this neural network that produce these word embeddings, which are embedding is in this case is the activations of observed on hidden layers for a given input low dimensional input word. The distributional models they assume a certain mechanism that exists behind or that reflects the semantic. So you make an educative guess of what how semantic is represented, and this would create a shortcut, kind of avoiding learning in the neural network sense. So connectionist models. So there are different ways. So like skipgram model. So you have a word for which you want to learn the embedding, and the output you present the windows, the window words, so the neighboring words to the left and to the right. So the context. And this is a kind of main approach. So that the word is modeled by the surrounding words somehow. So bag of words approach. So for example, implemented by Word2Vec model. So is the opposite. So you input the context and you try to learn the embedding for a given word. So both approaches have pros and cons, and different interesting experiments was demonstrated, like substituting, including vector manipulations to produce vectors similar to new concepts. But let's talk about distributional models. So it was kind of it goes back to end of 90s, and it was observed that I mean the model is based on observation of frequencies of encountering different terms in different contexts. So the original method, known as Latin semantic analysis, assume that you have a corpora of documents, like books or articles, and then you have the terms for which you seek an embedding, and then you basically count the occurrence of this term in the different documents. And you need to have a representative set of documents, and that would be to create a statistically reasonable word representation. But as you can imagine, technically, so this term means that you need, first of all, you may have a very large set of documents that you analyze, and then you may have a very large set of terms that you want to model. So you will have this huge matrix, which is rather sparse, which is quite bulky to compute on. So what this Latin semantic analysis technique does, so it does singular value decomposition, so extracting the kind of underlying lower dimensional matrix describing the terms. And already using this method, so here the learning is really kind of statistical. So the result on TOEFL synonyms test is 51%, which is not bad at all. So a modification to it, and that is somehow, so I collected the slides to smoothly transition to the topic of the next class, which is this high-dimensional random representation spaces. It modeled, or it approximated this method by doing the following. So all documents, so the IDs of the documents, they were represented by random binary codes of sufficiently large dimensionality. And again, looking a little bit ahead, or ternary codes, it could be binary as well. And the original idea is that, I mean, you need to have this rather large dimensionality, say 1000 dimensions, so that when generated randomly, so these vectors are pairwise dissimilar, or orthogonal, if you wish. And what you do then, so you have a table of terms initially initialized to all zeros, so you don't know the embeddings yet, and now you scan the document. So the idea is the same. So you kind of you want to implement counters of words in each document, but every time you encounter a term, so you add the ID of the document to it. So and since the original original IDs were randomly generated, so the embeddings, well, they will somehow statistically group with respect to the frequency of occurrence in this document, and reflecting the intrinsic similarity. And so that was kind of main improvement over the Latin semantic analysis, because you don't need to have a very large matrix for processing. So your embeddings are limited in dimensionality from the beginning. So by fixing this dimensionality of the IDs, and then you can use these embeddings directly to compare the similarity. And it achieved pretty much same score. So what I want to finish with is the next modification of this random indexing when so the idea was that to produce the embedding of the word, so the context of the document, so the entire document, is probably too wide. So it captures certain similarity, but maybe the context should be smaller. So and it's pretty much same idea as it was used in the neural network-based embeddings. So you focus on the not on the context of the document. So I mean, the analogous approach would be to input entire documents to a neural network, but you can imagine the size of this neural network and nightmare of training it. So here is the same idea. So you want to somehow create embeddings of the term, but not based on the occurrence in the document, but based on the occurrence in the context of their neighbors. And that's what you will look at in lab 2. Lab 2 is not very complicated. It's more of observational type. So you need to kind of looking at the code, well, execute it, test it, but also understand how it is implemented. And here what is happening. So now you create some initial representation of the words, of the terms, in a similar fashion as you generated IDs for the documents. And again, so as it will become evident next time, you can generate on large dimensionalities, like say 1,000 dimensions, you can generate as many dissimilar or orthogonal codes as you wish. So that dissimilar meaning that you can take any pair of words and their codes, check the dot product. So it will be very close to 0. So they will be almost orthogonal. And then you will discover what happens then next time, because it's very closely connected to hyperdimensional computing. So we continue next time.